Okay. So if you missed last week's talk, I've built them so they're independent of each other. So I alluded to this week in the question and answer session last week, but you didn't have to hear last week's seminar to know what's going on this week. I've cherry-picked from 3 lectures that I give in my Green Roof course, and I actually added on some information about policies at the end. I thought about it later and I realized policies are really what drives our industry, and we do have green roofs in Texas. Johnson Space Center in Houston has a huge one. There are 3 on campus now. We have a 4th one coming. I've talked to some city planners in Dallas and Fort Worth, and I know they have some as well. So they're coming, but our industry has not skyrocketed the way it has in other major metropolitan areas, simply because our policies have not yet started incentivizing them. I think it's coming, so I wanted to add that in at the end. If you're not from Texas, pardon me if you're bored, but you might learn something about your own policies, so I added that at the end. I do want to start off with what makes certain plants better than others for green roofs, though. So if you think about the green roof environment, it is challenging. It's man-made, and that's important. It is not a natural native environment. It is harsh. It is man-made. It is not meant to be for plants. We have made that for plants. It's hot, obviously. It is exposed. It is dry. If your green roof is irrigated, you can overcome a little bit of that. But we do want to always be water-wise, so there's a fine line there. It's very windy. You know, my buildings in Washington, D.C. and my former job, there's an ordinance in Washington, D.C. that you can't go over a certain number of stories in certain parts of the district, simply from a national security standpoint. And so my buildings were not that tall. I think maybe the tallest was 10 or 11 stories. But it gets quite windy still, even at 10 to 11 stories. So if you're in a metropolitan area where you can go higher, wind is even more of an issue. There's excessive UV radiation because there isn't much shade. And if that wasn't all good enough, there's a very thin substrate layer, typically 4 inches or less. If you start talking about going more than 4 inches, you're going to have a massive problem with maintenance, and we'll talk about that a little bit later on. So in our man-made environment, native is relative. And when it comes to plants and the native plant palette, there are 2 schools of thought. And one is, well, you should only ever use native plants ever because native plants are better and all non-native plants are terrible. In a green roof environment, you can't have that attitude and be successful because, once again, it is a man-made environment, so native is relative. That wasn't meant for plants, so a native plant on a roof, there is no such thing as a plant native to a green roof, okay? Now, it has to be available in the trade either as a plug or seed. You can have the most best perfect plant for green roofs in the world ever, and if it's not available in the trade, it just doesn't really matter. Now, all of you growers who are on the line, take note, because you might know of a perfect green roof plant that you think would do well in a green roof environment. I challenge you, please start producing it. Send it out there. One of the reasons our plant palette has historically been limited was we started out with the sole producer of these plants. Mr. Ed Snodgrass in Maryland has green roof plants, and he has done so many wonderful things. He is a plant collector. He goes all over the world collecting plants for our industry. But the ones that we started out with, that he started out with, first of all, are the ones that really became dominant. And so we've struggled a bit to incorporate other plants into the market. Now, these plants shouldn't create risk of invasion or escape. And this is largely regional. A landscape example I'll use is one of the most terrible trees I know, which is a Bradford pear. It's an ugly tree. It's short-lived, and it always breaks apart. However, if you like Bradford pears, that's okay. But along the East Coast, they have escaped. And if you drive up and down the I-95 corridor in the spring, it's quite lovely because there's just a sea of white flowering trees. Those are Bradford pears that have escaped, and they are literally choking out the native forest. That's not a problem here in Texas. It's a regional problem on the East Coast, so that's something you have to remember. When I give this lecture here, I like to use the example of bluebonnets for my students because they have to understand there is a difference between invasive and prolific. Here in Texas in the spring for a few weeks, anywhere you look, you're going to see a beautiful blanket of bluebonnets growing anywhere. They grow outside around our greenhouses. They're along the roadways. They grow in people's lawns. It's gorgeous, and then after a few weeks, they're gone. They are not invasive, even though they are everywhere, and they seem to be choking out everything. They're not out competing other species, and that's really what makes the delineation between prolific and invasive. Okay, so when we talk about heat and UV radiation, there are a few adaptations that some plants have that makes them good to withstand that. Pubescence, which is kind of these hairs, I'm going to use my pointer here. If you look at these little hairs here, this is collectively called pubescence. That can do a few different things. There are a few different mechanisms. The biggest thing is it increases the relative humidity around the surface of the plant, which decreases how quickly you're going to be losing water, water vapor through the evapotranspiration. They could also have a thick waxy cuticle. You'll see here these plants are kind of waxy looking, the leaves, so that helps. And then if you look at the leaf shape here, they're smaller, they're more cylindrical. That means there's less surface area on that leaf that's exposed to the sun or the UV radiation at any one time, and that's helpful. To deal with drought, first off, the plants have succulents. And man, this is so interesting. When I was preparing for my course this semester, I thought, you know, is there a scientific limit? Is there a fresh weight per dry weight ratio that determines whether or not a plant is a succulent? Because succulents are very popular now. Everyone wants a succulent container garden. You can collect them. They propagate very easily. And so it's something that has become kind of a hobby for a lot of people. But what makes a succulent a succulent? And I dove into the literature a bit, and I couldn't find an answer. There are actually scientists out there who believe that things like tulips and irises should be classified as succulent because their wet weight to dry weight ratio is quite similar to plants that we do call succulents. And so that's kind of interesting. There isn't an actual scientific delineation, but kind of everyone knows what a succulent is. They just hold a lot of water. Something that's cool about these plants is they have fewer stomata per square centimeter, and sometimes they only have stomata on the underside of the leaf. So the stomata, or the singular stomate, that's the opening where a plant harvests carbon dioxide for photosynthesis, and that's also where you can negatively lose water vapor through the leaf unwittingly. And so by decreasing those stomata and putting them on the underside, you can limit how much water you're losing. That helps against the drought. Now, this is the magic. The crassulacean acid metabolism, aka plants, are magic, and one day they will take over the world because they are so flippin' cool. I'm going to get a little sciencey, but it's important because I want you to understand this. Because if you understand CAM, or this crassulacean acid metabolism, you'll understand why Texas is so, it's going to be a struggle to get green roofs really to take off here, and I think this is why. Okay, so first we have our normal C3 photosynthesis. We consider this kind of the normal baseline because this was the first photosynthetic process that was discovered. Had we discovered one of the others first, that would be the norm. We did this one first, so this is the norm. We call it C3 because the first isolated identified product of this chemical reaction was a 3-carbon chain. 3 carbon, 3C, C3 photosynthesis. All right, so this is what it looks like. We all learned this in high school. I'm not going to get any more sciencey than this, but we know we take water. It's transported from the roots up to the leaves. Carbon dioxide, that's harvested directly through the stomata on the leaf. Remember, we said those have to be open to harvest that carbon dioxide, but then the catch-22 is you could lose water vapor. The sun, the light energy, is the engine that powers this whole process, and it's magic because you take a liquid and a gas and you get a solid and a gas, and it's just magic. Okay, so the problem here is if you think about having to harvest that carbon dioxide through the stomata, there's an enzyme that does that, and the problem with that enzyme is in C3 photosynthesis, it also harvests oxygen. It doesn't care. It can grab carbon dioxide or it can grab oxygen. If it grabs oxygen, there's a process called photorespiration that occurs, and this is really bad for the plants. If you think about photorespiration as the plants being on a diet, it's the same thing. So to lose weight as a human, we know that it's basically calories in, calories out. You need to eat fewer calories than what you burn. That's how photorespiration works in plants. The plant is literally spending more carbon to run the photosynthetic process than it's taking in through the leaves, because instead of taking in carbon, it's taking in oxygen. Studies have shown plants in photorespiration actually lose mass. They do lose weight, and that's a problem. It's a very inefficient process. The plant is literally consuming itself to keep photosynthesizing. So a C3 plant might not last long. CAM photosynthesis is an evolutionary adjustment, I guess, to the C3 photosynthesis that makes some plants better than C3. So one of the adjustments for CAM is the stomata are closed during the day to prevent water loss. That's magic because when the sun is up, it's more hot and you can lose more water through your stomates, so you just close them. Well, but the problem there is if your stomata are closed, how are you going to harvest carbon? Well, the carbon is harvested at night. So it's stored in the vacuole overnight as malic acid. But if you go back and look at that original photosynthetic process, it takes light. You have to have light to make that sugar. Well, the sun is not up at night, duh. So all of that carbon gets stored overnight until the sun comes up. When the sun comes up, the stomates close, but then the rest of the photosynthetic process can happen. Only instead of the plant eating itself, it's pulling carbon from that malic acid. It can continue photosynthesis without photorespiration. I told you plants are magic, and this is really cool, right? So, fun fact, many greener species, the sedum, a lot of the common names for those, especially in the UK, is bittercress. And they're called bittercress because if you eat the leaves in the morning, they taste bitter. Guess why they taste bitter? Malic acid, because they've been in CAM photosynthesis. Mind blown. All right. So there's a few different terms for this. So facultative CAM, those are plants that can switch back and forth between C3 and CAM, and that's what we're really talking about here, is those species who they can flourish when it's rainy or they can shut down in a drought. CAM idling is what happens when plants are just kind of hanging out in CAM. They've switched to CAM and they haven't switched back to C3, so their stomata are closed indefinitely, and they can hang out like that for a while. CAM cycling, that's the actual cycling back and forth between CAM and C3. So the next most obvious question here is what triggers that cycling? So for decades, scientists believed they did have data that it was a drought-based response, and we had a little bit of data for that. I like to call her my academic big sister, Dr. Alyssa Starry. She is now at Portland State University. She completed her PhD at the University of Maryland the year before I did. Whereas I was studying the greener substrates, she was studying greener plants, and she was trying to figure out what triggers this cycling. So she took one species that had already been proven to be a cycler and a species that we thought could be, but we weren't sure, and she tried to force them into CAM. And the first time she did the experiment, she failed. And she was a trooper. She did the experiment at the University of Georgia at Dr. Mark Van Urzel's lab, and she came back and she said, man, I couldn't do it. They photorespired the whole time, and I did everything I was supposed to do. You know, we didn't water them for days. And she came back and she checked the literature, and she found that she had to have a significant temperature change from day to night. And she went from 20 Celsius down to 15 Celsius for her day-night cycles, and those plants shifted into CAM just like magic. So that's what it took. So it's drought and temperature change. What are the implications for Texas? I moved to Texas on July 1st, 2015, and when I arrived that afternoon, it was 106 degrees. That night, the low was 88. I will never forget that. The nighttime low was 88 degrees, and I thought, where have I moved to? And I started paying very close attention to the nighttime lows in the summer here, and I realized people had told me, oh, you know, Texas green roofs look awful. They're always dead. I've never seen one that looks good. And I thought, oh my gosh, that's why. Our nighttime lows, they're not low enough. Our plants are not able to cycle into CAM to be drought tolerant. They're burning up. So I think that's what our problem is here. There's a few verified green roof CAM plants, Sedum album, Sedum spurium by Colleen Butler. Photomus campshotagonus and Sedum album were the ones that Dr. Lissastari were working with. But we think most of the Sedum species have at least some propensity to CAM cycle. We haven't tested all of them, but we can assume with pretty decent certainty that they have a little bit of that functionality. Okay, back to the man-made environment. Wind. That pubescence increases the leaf-adjacent relative humidity, which also guards against wind, and they're short-statured. And that makes them more protected from drying winds. Think about what types of plants grow above the timberline and what those same species look like below the timberline. When they're above the timberline, they're typically more short-statured. Do all green roof plants have to be short and pubescent? No, but there's a reason that most are. The other thing is there's a very thin substrate layer. You need a fibrous root system for multiple reasons. One, you need a fibrous root system is going to be less potentially damaging to the waterproofing membrane. That taproot is not going to be able to travel down around and get into the drains. They're more efficient at finding water in shallow media, and the biggie is that fibrous root systems are more efficient at holding that media in place against wind uplift because, again, wind is a problem. So the other thing you need to remember is you need a relatively low biomass, meaning all of your plant material above the soil line needs to be relatively low. The reason for that is fire. Fire codes are a thing, and if you have a whole lot of biomass up there, fire can be a problem. We do see some use of ornamental grasses on green roofs, but that biomass needs to be cut back and removed every fall so that it can grow back fresh and green and less likely to burn. Okay, the other thing here is nurse plants. So I mentioned Dr. Colleen Butler had done some work with CAM cycling. She reported improved plant health in non-sedum green roof plants when they were grown adjacent to sedum. So the moral of that story is, if you want to expand the green roof plant palette, you can't entirely abandon the tried and true proven species. The problem here in Texas is, I just told you some of the reasons why these traditional species always fail here. Unfortunately, those are the species that we have readily available to us on the market. There are thousands of sedum species around the world. The ones that we use in our industry today natively grow either in more colder latitudes or up in mountains. So they have those temperature fluctuations at night. There are sedum species that are natively from warmer climates that don't have those cooler night temperatures. I think in the Southwest and in Texas, we're going to have to start considering those. Growers, get to growing. I think there's a solution out there. We just don't have it available in our market today. These are my Texas green roof musings. I've already kind of said all this. Establishment via seed or a combo of seeds and plugs is likely the best option here for Texas. Talk about why. We need to expand our plant palette beyond what is readily used in the industry, and we need to embrace nurse plants. We have a lot of Texas natives and wildflowers and plants that are adapted to drought and dry conditions, but we need to utilize some nurse plants. But first we're going to have to identify which nurse plants can handle the drought and not burn themselves up. The big thing here, we need to reprogram architects, designers, and building owners to expect our green roofs to look different. our green roofs here in Texas are not going to look like the pretty brochures that are used everywhere else in the country, because our green roof plant palette is going to have to be different. Once we can reprogram that sector of our industry, I think we will flourish. But as long as we're trying to make our green roofs look like everyone else's green roofs, they're going to continue to fail. I was in a meeting yesterday with a grower, and he said, oh, I missed your webinar last week and I wanted to catch it, but you know, I've seen green roofs, and every green roof I've ever seen around here is ugly and it's dead, and I just don't really think they're going to work for Texas. And I said, man, you need to listen tomorrow, because we're going to talk about why that is. I think here in Texas, it's going to be a little bit less about stormwater and a little bit more about energy efficiency savings. When you have a green roof on your roof, you get a huge benefit in the summer heat, and obviously that's a problem here in Texas, the summer heat. So I think we're going to see more regulations about that maybe than stormwater. The nighttime temperatures are going to kill us. They already are. So embracing seasonal and rotational plantings is likely a good starting point. I would love to see some sort of a self-seeding plant palette, something that maybe it is just an annual, but that it self-seeds itself readily. And it just rotates from season to season. Maybe in the spring you have bluebonnets. Lupines do like dry areas, and then they go into something else, into something else, into something else. And amongst that, you have some sort of a succulent species that can grow. I think that's where we need to go. Maybe if someone will give me some research dollars, I can start working on that. Okay, next we're going to talk about green roof maintenance. This is going to be pretty quick. You have to maintain your green roofs. If you don't maintain your green roofs, in a few years it's going to look like this. Sedum are not competitors. They are happy to grow where other plants typically can't. But if other more competitive species like grasses can take hold, they will outcompete your green roof plants in a heartbeat. And this is what happens. So this is a green roof that wasn't maintained for several years, and you can see some grasses up here, but you see this great big dead area, and then you just have patches of sedum. This roof wasn't maintained, so grasses and clovers and other non-competitors took over, and then there was a drought. And when there was a drought, everything else died, and then this is what you get, and then you're susceptible to wind uplift because you have all this exposed media, and it's just a problem. You can have microclimate issues. So here we have LEED certified windows. LEED loves these windows. They're low E, which means they're highly reflective. They reflect more of the UV radiation, so the offices inside stay cooler. The problem is you literally cook your plants. I mean, like they're baked. They're just, even the sedum are having a hard time in this environment because all of the UVA radiation. So if you're listening to this and you're a landscape architect or a designer or a building architect, please think about how you need to design this green roof to be more competitive against these kinds of problems. Okay. Species diversity is not constant. I've been talking about needing a mix of plant species. Contractually, if you're going to be taking care of or installing these things, don't guarantee a ratio of plants and don't guarantee a specific species. Just guarantee healthy plant coverage. You need to plant a mix because that roof ecosystem is going to adapt and ebb and flow in drier and wetter seasons. My most healthiest roofs that always looked good never looked the same twice, from month to month or from season to season, because sometimes the narrow-leaf sedum were happier, sometimes the broadleaf sedums were happier, sometimes my wild allium that were just volunteers that we left, which are growing here, sometimes they were more prolific. We didn't care. We had healthy coverage. Maintenance 101 for easy roofs. We made a visit every 4 to 6 weeks. Doing so meant we were more likely to catch weeds before they went to seed. Of course, if we had a rainy summer, it didn't matter. We were going to have a weed cycle every time it rained. Every visible weed was hand-pulled on a visit. We could use a pre-emergent herbicide if some weeds had gone to seed. You just had to know that this is going to inhibit sedum because sedum do naturally seed themselves, and so that was going to get them also. We soil tested annually and applied controlled release fertilizer as needed per the soil test. Reclamations. Most of my book of business actually were roofs that went unmaintained for multiple seasons, and then they called us because they knew that we knew what we were doing. Unmaintained green roofs need to be visited every 2 weeks to get on top of those weeds. At these visits, it's important that as you're pulling the weeds, you're taking pieces of those sedum and spreading them around because they will readily root in. You just have to help them out to get spread around. Soil tests and fertilize as needed. After 2 seasons of those biweekly visits, it should be in pretty good shape. Of course, your client is going to panic at the cost of all of that labor, but if you give them a choice, give your client a choice. Say, hey, you know, we can do this the slow way, and I need at least a 3-year contract, or we can do this the quick way, and we can go in and scrape everything off and re-put down clean media that isn't infested with weed seed and plant you a brand new roof. And this is the cost for those 2 options. I promise you, your client is always going to choose the slow route because it is less expensive. Green roofs and irrigation. If you use temporary overhead irrigation to get your plants established, they're going to get established pretty quick, and then you can pull it forever. You can utilize permanent irrigation to expand your plant palette. Please don't, one that's not water-wise. I do think that even in Texas, we can find a plant palette that is successful in our heat and droughts. We just have to find them. One of our very visible and pedestrian accessible green roofs had permanent underground irrigation, but it was in 4 inches of media, and those were 1.5-inch main lines in 4 inches of media. There were so many broken lines and heads. People would kick the heads. In the winter, people would walk across the roof and not stay on the footpaths. And when the media was frozen and they would step on frozen media, instead of your foot pressing into that media like in the shape of a footprint, it would kind of press down as one firm sheet, and that would pop the lines. My very last week of work, which was in June at my last company, I was replacing main lines on this roof, and some of those lines were shattered a length of 15 feet where people had walked on them. So if you're going to do permanent irrigation, you have to think about all of the long-term ramifications. Okay. I'm going to move now into public policy regulations and how to predict performance. I'm going to be pretty critical here. I'm just going to say it like it is. I'm very, very critical of the way, not all, but the way some policies have been written because they're wrong. And there is no other way to say it. And I've talked to some of the policy writers in the state of Maryland. I'm not going to name names. They knew that some of their things were wrong, and they just didn't want to go to the work to correct it, and that was what the one person said was we just knew it was going to be too much work to change it, so I'm going to call them out here. All right, green roof costing. These are East Coast numbers as of 2015 and are almost certainly different now. I'm just showing you the example that a traditional roof, this is just your waterproofing, maybe you have a ballast over it depending on the method. $17 to $20 a square foot. Green roof, $35 and up a square foot. This is average. We had less expensive systems and could finagle the cost, but that decreased the depth of media and also limited our plant palette. This is just to show you that green roofs are not cheap. They're not supposed to be. You're adding something that wasn't there before. So green roofs have been incentivized by state and local municipalities to get them incorporated into construction because it's expensive. Most green infrastructure costs are passed directly to the building or property owner. These are things like green roofs, bioretention, cisterns, detention and retention ponds. Whoever owns that building or property has to pay for the cost of these. Gray infrastructure, things like pipes, concrete ditches, the cheap, fast way to move large volumes of water, those costs are passed directly to the taxpayers by way of fees and taxes. So if we want to do things that are good for our environment, you have to talk a building or property owner into going to that extra cost. And as you can imagine, that's not easy. So now we've seen an increase in subsidies and rebates, tax credits, grants, stormwater credits. Different states have different means of incentivizing green infrastructure and green roofs. Various Texas towns have incentives already for rainwater barrels and cisterns. So I think green roofs are coming next, but we'll see. So how are stormwater credits determined? Now, this is where science and policy have to meet, and unfortunately, they do not often get along. The big thing these days in commercial construction is pre-development hydrology, and I'm gonna talk you through this graph. That is to say, for example, in the state of Maryland now, if you want to be permitted to build on a site for commercial development, you have to prove before you receive your building permit that you're going to return that built site back to its pre-development hydrology. And here's what that means. So this is a hydrograph. What we're looking at is stream flow over time after a rain event. So this solid line with the blue under it, this is stream flow for an undeveloped site. It's wooded, there's grass, there's no impervious surface like concrete or asphalt. So the stream does swell after a rain event, but it's not very much, and it just gradually recedes. Once you've developed a property and put impervious surface like rooftop concrete and asphalt on it, when it rains, all of the water rushes very quickly into the stream and you get a peak. And then it goes down after that. This peak is very damaging. We're not going to get into that. It just is. Just take my word for it. And that's what we're interested in controlling. Okay, so most of your municipal, state, and federal policies are based on pre-development hydrology, and that means the standard of measure has mostly been a reduction in this peak flow. Now, that's good and bad. The good is we're reducing that peak flow. The bad thing, we're mostly addressing runoff. We're not considering shallow interflow, and that means the water flowing three-dimensionally under the water. Under the soil, and groundwater recharge. And I'm going to use Lubbock, Texas as the example. I visited Lubbock for the first time last October to speak on campus, and they were showing me some areas where they had some flash flooding issues, but then they said, you know, the big thing is our groundwater recharge because we only have a couple of years of water left in our local aquifer. That's terrifying to live in a very quickly growing metro area that has, oh, we just have a few years left in our local water supply and our aquifer. That's terrifying. And so these pre-development hydrology approaches are not considering that. But for better or worse, the standard of measure has become total water retained or detained. Okay, so what about green roofs? Well, regulatory agencies have focused on water quantity, the total volume of water, and stormwater credits are granted to green roofs based on the quantity of water they hold. So these commercial developers can say, hey, I'm going to put a green roof on my building, and that's going to account for X volume of water, and if that can get you back to your pre-development hydrology, you're good to go. Now, these quantities are estimated at the time the regulations and policies are written, and they are applied to construction permitting until those policies and regulations are rewritten or amended. Now, how do these regulatory agencies predict green roof performance? There's kind of two different methods out there. One is just absolutely wrong, and one is better, but it's still not perfect. Okay, so first we're going to talk about curve numbers. Most of you may not have heard of a curve number, so I'm going to give you a crash course. This method was established in 1954 by a scientist in the Soil Conservation Service. That scientist meant this to be an interagency estimation of runoff. That means they never meant it to go outside of the SCS. They were only going to use it internally. Furthermore, it was developed as a tool to be applied to agricultural fields for agronomic crops, wheat, corn, soybeans, deep terraced farmlands, okay? It was never subjected to peer review, nor should it have been, because it was meant to stay inside the agency. So that's not the fault of the scientist or the agency. It's the fault of all of the rest of us who adopted it willy-nilly. Nor was the method ever tested for accuracy. No one ever ran a curve number equation on an actual field and then went back and double-checked it to see if it was right at that time. So that, again, is not the fault of the agency. It's the fault of everyone who adopted it after the fact. That curve number method has now been widely adopted by regulatory agencies to compute peak runoff rates in urban applications, not agronomic, urban, cities. Okay, so like what is it? It's a number between 30 and 100 that relates total precipitation, so the number of inches that falls in a rain event, to its potential to run off. And I'll show you how that works later. Basically, you account for evapotranspiration, absorption, and surface storage, and then it gives you the result of your runoff. So there's a mathematical equation. I'm not going to show you the equation because I don't want to further spread bad information, but you can Google it if you want. You pick the number of inches of rainfall, you pick how much surface storage you think you're going to have, and you pick your soil type. And you plug those things into the equation, and it gives you your curve number. The higher your curve number, the higher the runoff potential. If you pick various precipitation depths and storage values, it will give you something like this. And here's how it works. So here's our rainfall in inches, and here's our inches of what we think our runoff is going to be. So a curve number of 100 here. So for 4 inches of rainfall, you're going to get 4 inches of runoff. For a curve number of 70 here, if you have 5 inches of rainfall, you're going to get 2 inches of runoff. So that's how this works. And that's why it's called a curve number, because these are curves that your rainfall and runoff are following along. Okay, so that's how it works. Now, why doesn't this work? Well, storm intensity is not considered, neither is antecedent moisture. Antecedent moisture is how much water was in that soil when the rain event started. If it hasn't rained in a week, you're going to hold more water than if it rained the day before. It's hard to account for that, and we probably never will be able to from a regulatory standpoint, so I'm not critical of that. However, I'm critical of this because evapotranspiration rates vary wildly amongst species. That's not considered. And all of these soil values are agricultural. Here's a news flash. Green roofs do not use type A, B, C, or D soils. We use engineered media. So this is it's just all wrong. It's all wrong. I don't know how else to say it. This is the nation's worst green roof stormwater policy, a case study. I pulled this screenshot directly out of the state of Maryland's current stormwater manual, table 5.4, and here's how this works. So this is your green roof media thickness, 2, 3, 4, 6, and 8 inches of media, and this is the effective runoff curve number that they have computed. Here's this, you can compare. Now, the state of Maryland requires pre-development hydrology, and the number that the state of Maryland picked was 77. Now, it's not bad that they picked 77. What's bad is that they assigned 77 to an 8-inch depth of media, which means now if a building developer is going to put 8 inches of media in their green roof, they automatically have pre-development hydrology. This is bad because, as we said before, green roof plants are not competitors. They like to sit in a place and grow where they're not going to be outcompeted. If you put 8 inches of green roof media on a building, it's going to grow everything. I know because I've seen it. It grows tree seedlings, grass, clover, all of the things that can grow in a 4-inch system. We have these problems in 4-inch systems, but you double the media depth, and boy, you better be visiting those roofs every 2 to 3 weeks because you're going to get outcompeted really fast, and in a rainy season, you're not going to be able to keep up with it. If rainwater and stormwater retention worked this way, we could put 15 inches on any roof and we would never have a stormwater problem. It doesn't work this way, but however, unfortunately, this is how Maryland works. So the moral of the story is curve numbers are somewhat useful for ag production. They should never be used for urban systems. Unfortunately, they are used to predict urban hydrology rampantly across the United States. Now we're starting to see a shift of entities using a different method, but some entities obviously do still use this wrong method. So a few agencies have written varied approaches that relate your substrate water, maximum water holding capacity to green roof depth. And that kind of makes sense. The maximum amount of water your substrate can hold in some relation to the depth of your substrate would be a little bit more accurate, because that accounts for your green roof media properties instead of assuming agricultural soil properties. The problem here is often the lab analyses that they use to determine maximum water holding capacity requires 24 to 48 hours of soaking that substrate in a water bath. When you do that in the lab, you often get results of 40 to 50% volumetric water content. My dissertation data when soaking gave me almost 60% volumetric water content. Actual field data in the literature has never reported over 33% retention. My field data showed a maximum of 22% volumetric water. This was during Hurricane Sandy when it rained for 72 hours straight. And this is raw data. This is snowmelt, and this is snowmelt. So we're looking here. This is Hurricane Sandy at the end of October. All the way over here, these are volumetric water contents as a decimal. So this is about 22%. Here's 20. Here's 30. I didn't even hit 30%, even though I tested the same exact media taken from the same sample that I mixed for my field plots. When I soaked them, I hit almost 60% volumetric water content, more than double what my field study showed. So this means regulatory agencies are overestimating green roof performance by millions of gallons each year because they're ignoring the rule of generally you're not going to get over an inch of retention. And that's the rule of thumb. But these agencies are ignoring that. They're saying, hey, we can get more than that. It doesn't matter if it's over an inch. We're going to get up to 50%. Now, it's not likely to hurt the green roof industry in the near future. The problem is in 30 years, we're still going to have a problem that, according to what we're selling now, should have been solved. Now, back to Texas. Is this going to affect Texas? I think it's going to depend on where you are. My guess is that in major cities, stormwater and stormwater regulations are going to be the driving factor, especially in a city like Austin. Austin is bursting at the seams. There quite literally is no physical space for the size and quantity of bioretention cells needed to be effective. So I think in Austin, you're going to see a similar approach to what you've seen in cities like DC and Philly, where they start incorporating green roofs and bioretention cells into their stormwater approaches because they don't have enough space for just bioretention cells to do the work, and green roofs can't do all of the work, so they're going to have to use a conjoined effort. In other areas, especially the Southwest San Antonio area, Big Bend, I think it's going to be energy efficiency. Unfortunately, this is going to be at the expense of the property owner rather than the state. Stormwater is a state problem because flood damage does cost the state money. Energy costs, that's a personal problem. So then it's going to just be left up to the individual building owner to decide, okay, hey, my 7 to 9 year return on investment to pay for this green roof based on my energy savings, that's worth it to me. And remember, those numbers came from a model that we discussed last week. Dr. DJ Saylor ran that model. It was published in Building and Energy. Oh, hey, that's the end. So I guess now I can open it up for questions. If there are policymakers on the line, I'm sorry, please don't kill me, but the facts are the facts. So does anyone have any questions?